Everybody, today we have a strange looking problem with a very odd linear coefficient. It's actually a finite geometric series with an unknown upper limit of integration. Let's just write down the first few terms. 4/3 is the first term when I is equal to 1. I is the index of the summation. And then when I is equal to 2, this becomes what, 16/9? And again, what I'm writing down is the coefficient of x in this quadratic. And then what do you get when you cube 4? You get 64. When you cube 3, you get 27. Or if you multiply 9 by 3, you get 27. So that's 64/27. Okay, and so on. Now, and the and so on is what we're trying to find today. We're trying to find k, which is the upper limit of integration. And again, this is the coefficient of x. Now, we are given a very valuable piece of information. The sum of the roots, or the zeros, of this quadratic expression is 781/243. Okay, so let's move along. Now, problem like this, it's almost instinctive or reactive to divide through by the coefficient of x squared to get what we call a monic polynomial here, degree 2. And we end up with this expression right here. Okay, now a lot of you are thinking Vietas, and you're right. Vietas is an approach here. So let's see why. Let's just go ahead and talk about, if you haven't heard of Vieta's result, it's basically as simple as this for the quadratic case. Just assume this quadratic has two real roots, or two roots. It doesn't make any difference if they're real or not, I guess. But we'll assume that it has roots R1 and R2. Okay, so here we go. And I said they're roots, so let's set this equal to 0. So when you expand this out, you get x squared minus the sum of the zeros, and it's minus the sum of the zeros. The minus sign sticks around. If you look at how that expansion would go, R1 plus R2, and it's minus the sum of the roots. That's the coefficient of x. And then the product of the roots is your constant term. Of course, that's equal to 0. Now that gives us some guidance here on how to proceed, because we know right now that, let's just write it down right up here, I guess, the 781. So we know from our work down here that 781/243 is equal to minus the sum of the zeros. Okay? Because it's given. The sum of the roots is this. So you have to write it like this. 781/243 is equal to this. All right. Now, so how do we proceed? Well, here we go. When you set this, wait, did I say that? I'm sorry, folks. The sum of the zeros, that's a mistake. That would just be, it's not minus, is it? That we're given that the sum of the zeros is positive 781/243. My mistake, okay? So let's go down and see what happens here. Now, but we use that information. R1 plus R2 is equal to 781/243, right? And so we get this statement right here. Okay? We get this statement right here, minus the minus sign here and the minus sign here are going to cancel out, right? And so we end up with this statement right here. Okay? And you see how it's going to work out for us nicely here? Well, maybe not so nicely. Notice that, let's see here, I guess this part right here, 4/3 minus 1. That's equal to 1/3. And notice what happens here. So this part's just equal to 1/3, right? So you invert and multiply, and you're just left with this. Okay? That's kind of nice. So, but it's nice looking, but we can't really solve this just directly with um, the the Lambert function. There's something called the Lambert function that would come in handy on a problem like this. Now let's get we need to get our numbers down here, right? So this is equal to 781 over 283, right? This is equal to 781 over 283. $243, whatever I said. Okay. Now, so again, you could try to do this numerically, but you know from the nature of this setup is that k is going to be an integer. K is going to be a positive integer. In fact, we can call that z plus if you want. Okay. All right. And so we could try to pick a k that works out nicely, meaning that it would, if you choose the right k, it would cancel with this 4. And just check the answer. That's not a guarantee it would work, but it's the best try I know outside of doing it numerically or using that the Lambert function. Okay, the Lambert W function, whatever they call it. So take a look at what happens here if we do k equals to 5. Okay, if we pick k equals to 5, this just becomes 4/3 raised to the k power minus 1. Now again, we want to check to see if this is true. We're checking to, I'm not saying, in other words, we want to know, is this true? It's a check condition, right? We're checking to see if this is true because the other ones would result in fractions that would seem to interfere with the 243 is what, 3 to the 5th? And so this is a reasonable try. So let's see what this ends up being. This would be 1,024 over 243. Right, when you raise 4 to the 5th power, you get that that's 2 to the 10th. 3 to the 5th is 243. Now we'll go ahead and just say minus 243 over 243, right? But that sure looks like it's equal, right? If you subtract 243 from this, don't you get 781? 781 plus this number, right? 781 plus this number is 1,024, right? So this checks. It works out. This is equal to the 781 over 243. Okay. So k equals 5 does work. Now I agree. I didn't solve this in so-called rigorous fashion, but it's kind of like integer programming. You know, if k was anything other than 4, maybe some other multiple of 4 is something you could try also. You know, but we've already found a solution. K equals 5 does work, albeit this method is not too confidence promoting, you know, but it still does check out. It is the solution, I believe, and there may be other, you know, complex solutions, but anyway, k equals 5 gets the job done for this problem. Okay.